This current material is about control volumes. So here's a little warm-up problem. This is just a pedagogical. It's not going to be on the quiz. But it tells you that there's basically two types of acceleration. So this is a pipe that's increasing in area, going from 4t, so 4 times time. So if you've got time equals 0, it's 0. Time equals 3, it's 12. So it's increasing with time. 4t, and this is 2t. And you can tell the second one's a little lower because of conservation of mass. Basically, you have a diffuser. The second one has to be lower because of large particle square area. So we'll see when we derive the definition of material derivative that there's two types of acceleration. A local acceleration, which is given by the time-dependent part, and then this is new for you, what's called the convective acceleration. And that means acceleration that takes place when you consider fluid transport from one point to another. We're basically going to consider the acceleration on a fluid particle. So I'll explain what that means when we do the derivation. But before we do this problem, let's go over what's going to be on this next quiz. So, in fact, for the next month, we'll be doing what's called control volume analysis. Okay. And we're splitting it into two parts. But in fact, they actually all use the same equation, what's called Reynolds transport theorem. They just use sort of different quantities that you're trying to track. So this will be in about 9 days. And then we have quiz 5 kind of builds up on this quiz. Angular momentum and energy. You don't need to worry about that for now. To be honest, I think if you really understand quiz 4, quiz 5 should be easier because we're really just tracking slightly different quantities. Okay, so there's a couple concepts that you're going to have to know what they are. For example, like the streamline for Bernoulli's equation. But I'm not going to be able to test you on definitions of these. We'll be talking about them today. So today, and in fact, this problem on the left, when asking about accelerations, is called fluid kinematics. Kinematics is distinct from forces because you're not asking how much force, how much pressure is on an object. You're just asking how the positions change with time. And there are basically two different approaches that we'll talk about. The second one leads to the governing equations. Eulerian approach, which is what you're used to. This is probably what you've done in, Howey, House of Pain, all these other areas. Eulerian means you're fixed in space. So basically, coordinates are fixed in space, and you calculate the derivatives at fixed points, in space. Now, what some of you are going to have to get used to is this new approach, which is what the governing equation is based on. It's called the Lagrangian Approach. And that's where we get these things like convective acceleration. It's when we're tracking particles. So moving with a particle. I'll say moving with the fluid. Okay. So you're tracking set parcels of fluid that are going to be moving. And I'll talk about those two concepts in a little bit. All the governing equations are based on this new derivative that follows particles, follows moving objects, and that's called the material derivative. But I call it like the big D derivative because you use a big D. I don't know why they decided to do that. Kind of, but it's an operator that says you take the big material derivative of something. It means you're taking the partial derivative with respect to time plus this convective derivative. U dot del, U is the velocity vector, tells you how much the fluid is moving, And basically, this is how much the fluid is changing with respect in the direction of the velocity. All right, Reynolds transport theorem. All right, so those are the sort of definitional things that we have. Now, the control volume approach, you basically have to distinguish between two things, the system and the control volume. The system is particles that are moving. I'll draw a little picture in a bit. And the control volume is something that's fixed in space. And the big thing that we're going to be deriving today, and what underlies all of these control volume problems, is called Reynolds transport theorem. Reynolds transport theorem relates how a system of particles, whatever behavior you're trying to track, their mass, their momentum, their angular momentum, their energy, to how much that's basically changing inside the control volume and how much it's fluxing in and out. Okay. Flux, and this is the time-dependent part. And this is also the first part of the course that I'm actually going to start to give some equations on the top of the sheet. Because the integrals can be harder to remember. All right. And we'll prove those, and we'll be talking about these. Now the homework, which I hope, the homework is really, the homework I'm giving you basically. I didn't have homework in the previous years. I only gave it to you so we could help you learn the material. But you got to not sort of get blind about just like copying the answers. You really do have to think about each thing, each step. There would be two types of, for example, this quiz will be two types of problems. One, conservation of mass, the other one, conservation of momentum. So the first one, the homework is about mixing of two pipes. It should be quite straightforward to do one of these things after. But if you got a Q1, a Q2, what is a Q3, and what is the density of it, things like that. I'm going to do this homework problem in class, either end of the day or next time. But if you've got a leaky syringe, so what if you basically got Q1 and Q2, stuff that's leaking out the front and the back? What can you say about how quickly you need to push the syringe? We'll talk about the rates to fill a container. So notice all of these three types of problems do not ask for forces. They don't ask for how much force is being applied. So that means they're conservation of mass problems. Conservation of mass tracks how quickly something happens. What is the new flow rate of something? It doesn't ask how much force is applied. And there'll be one problem in the quiz that probably involves conservation of mass. Certainly, you have to use conservation of mass for each of your problems. Just like for every Bernoulli problem, you have to use conservation of mass to solve for it. Now, questions that are more obviously conservation of linear momentum are like this. Force on a bent pipe. So, for example, fluids coming out at these two arbitrary angles. What is the anchoring force on the pipe? How much force do you, how strong do you need to make the little screws so that thing holds in place? And the big physical idea why you need an anchoring force is that fluid's coming in one direction and it's turning and leaving in another direction. Fluid's got momentum. Just like if there are basically like a million little ping pong balls going in and you're turning them, you're required to have a force to change their course. So force on a bent pipe or an angled plate, the concepts are very similar. The only difference between for an angled plate is that there's no, or this is an angled plate. This is a free jet, so you don't have to consider the prospect pressures. Emptying container. So actually, we'll talk about rockets and how they worked. Emptying, but if you empty containers, there's a force on them, not just due to them getting lighter, but also due to the fact that fluid's leaving from one end. And there's a problem in the homework about sluice gates. And so these problems are conservation of mass, of linear momentum. I'm probably going to use the word mom for momentum later, just because it's going to get long, but I'll write it for the first time here. So you'll need to practice Cartesian and polar vectors. We'll be going back to polar coordinates in quiz 6 and 7, so they'll be coming back into the course. We haven't really used them yet, but just be aware. All right. Any brief questions on like what I've talked about? I know this. I will be explaining these more in depth. But so as you can see, there's actually a decent amount of material for this coming quiz.
For the material derivative, on that last, I guess on board 2.
Yeah.
Is that velocity dotted with the gradient in the equation?
Yeah, it is. Where velocity is as usual ux. Okay. I'll call it u comma v comma w for the x components. We can consider ux, uy, uz. You have 3 components. And gradient is a vector whose components are derivatives in each of those spaces. Okay. So u dot del is a sum. I will go over that. U dot del is basically a sum of something that you operate, whatever you put into the big D. All right. And this vector calculus notation quiz, the last quiz of the course, is sometimes going to be a little tough for people because it's also near the end of the term. But that is where we do the Navier-Stokes Equations. Unlike other fields of physics, we actually have governing equations for fluid mechanics called the Navier-Stokes Equations that tell how fluids are going to behave, pressure and velocity fields evolve, and involves this convective derivative again. So we'll get back to that. All right. Okay. All right. Okay, so let's talk a little bit about what these terms. So I used to have some quiz on chapter 4, but really chapter 4 is just to tell you definitions so you can actually understand where these equations are motion. So chapter 4 is about fluid kinematics. And like I said, kinematics is just a fancy word for things that are functions of position. It kind of means the word motion, I think. But basically it involves position, velocity, and of course the derivative of velocity, acceleration. But not force. Force, anytime we bring in force, we have to use Newton's law, F equals ma. So this is everything that you do until you get to F equals ma. So this is where some of your different equations, representation. Difference equations, you basically represent everything as, a partly Cartesian field. But we're basically going to say any fluid property is a function of space and time. Where x, I'm going to use the notation x underlined to be the vector x as a function of time. Okay. All right, so let's go with a little picture first. All right. So let's say we have a fluid particle here. I'm making it a really big dot. We'll call the position of it r, and we'll label the particle A. So this is particle A. And for the first two parts of this course, well, for hydrostatics, everything was static. Nothing was moving. So to figure out the forces, we just had to look at stuff in space. But now the fluid, this particle is flying along. Like if I cough without my mask, like my slide particle is going to float around the room. So it's going to be moving like this into a new position, r sub a t plus delta t. All right. And this is the particle path. And so this picture kind of, hopefully it'll remind you a little bit about the warm-up problem. We have fluid going through that pipe, and starting on the left and going to the right, just like this particle. And when it does that, it's going to change in velocity because of a time-dependent part and a basic convective part. So just in terms of regular space, we basically got the velocity vector u is a function of the position x and time t. And to write that out in more detail, basically the x component is going to look like this, and then the y component, the v is also going to be a function of x, y, z, and times y hat plus w, x, y. And you can see why we're using this vector notation, because this is incredibly cumbersome to write this. But that is in fact how stuff changes. Basically, the horizontal u is the horizontal velocity. The horizontal velocity is a function of, x, y, and z and time, and same with the vertical, and same with the velocity into the board. So this is the Eulerian approach, where basically you look at fixed, x, y, and z fixed points in space, and the Lagrangian approach, which I'll define on the next board. Basically, we try to figure out what the velocity of this particle is, and we have the definition that that its velocity in face of this thing is a function of time. And ultimately, the reason why the convective derivative comes about is because not only each of these components are a function of time, but their positions are a function of time as well, because it's moving. Let me give people a chance to copy and I'll move boards first. So the whole reason why we need convective derivatives is because, you can imagine, like I made the example of the spit particle that comes out of my mouth. It could be slowing down just by the fact that, it's everything in the room is slowing down, just like in this problem. Things are a function of time. But it also could be going to a place in the room where the velocity is slower. Let's say it goes towards the ground, there's less people walking there, and the velocity is slower. And that's essentially, those are two independent parts, and that's why we have two different parts of the acceleration. So I've been using this Eulerian and Lagrangian terms. Let's just define it.
think you should switch board.
Oh yeah, let me do it now. All right. Discard fluid. So information is collected at fixed point in spaces, fixed points in space as fluid flows past. And there's a whole area of fluid mechanics called Lagrangian fluid mechanics. All right, let's give two examples here. So let's go over these. So let's look at the example of birds migrating. Let's say you want to measure a bird migration. Now, birds are a good example because they're actually flying around. They're moving in space. So if you want to do the Eulerian approach, what you do is basically, someone would stand in the middle of Turner Field and count the number of birds that are passing by. So this would be counting number of birds passing Georgia Tech. So literally sit there and you're not moving and you're just counting them. And that's essentially what we do with mass and momentum and angular momentum and energy. We're just counting the amount of those quantities that are passing by. They're not birds, but they're quantities. In the Lagrangian approach, would anyone be able to say, how would you do a Lagrangian approach for bird migration? Yeah?
Tagging or following a specific bird.
Yeah, that's exactly right. So that's like a radio transmitter on one bird. And that's also an approach people do too. On a bird. And the key word is this tagging. Kind of like a gang would tag a truck, spray paint it. But you want to basically literally imagine it's a different color. And you're basically stuck to those particles and they're moving. All right. And when we basically go with a Lagrangian approach, there are basically, like I said, two reasons why things are going to change. One, because the whole velocity field is going to change, and the other one, because you're going to a different place where the velocity field is different. If you get that concept, the derivation will not be so hard. So that's the physical intuition of it. Now let's go through the math for why there are two types of acceleration.
What's that symbol underneath?
The number sign, hashtag.
No, birds passing. What's that last?
Georgia Tech.
Oh.
Georgia Tech. Oh, we're going to draw buzz. That's probably one of my better ones, actually. All right, given a velocity field.
Could you change the board?
Oh, what?
Could you change the board?
Oh, yeah. All right, so given the velocity field, what is the acceleration field? And there's some warm-up problems in the book that they give you numerical equations for the velocity and you calculate the acceleration field, but those are too easy for the quiz. And to remind you, like back in when we did Eulerian coordinates, in House of Pain, this was very straightforward. You just took the time derivative of it. But now stuff is changing in space, so it's not that straightforward anymore. So let's go back to our picture. So that's our particle moving. So it's going to have now some velocity of that, it's tagged A, like some gangster just painted it in red. And it's a function, that velocity is a function of where it is, which is R vector, and time. Okay, and just to remind you, we'll have this notation XA, YA, ZA. Okay. And we'll call this UA, VA, WA. So I'll stick with the same notation that UV and W mean the velocities in those three directions. So we got the particle velocity, UA is function RA, time is equal to UA. All right. So I'll just write what we have up there, but we'll give some meaning to it. So the velocity of this particle A, it's a function of where it is in space. This is the location. And it's also a function of time. And those are sort of two functions of time. One just of it's a function of time, and one of where it's in space. Okay? And we need this one for unsteady flow. Things that are, just like in the warm-up problem, things that are basically a function of time. All right. Now, the acceleration I'm getting a little sloppy. So the total derivatives are the non-squiggly ones. This is partial derivative because u is a function of all those variables. So it means you're just taking it with respect to that part. One you see, you just do the rest of your seats. I'll fill it in. You gotta use what's called the chain rule. Chain rule, just to remind you, d dt of f of g of t is is equal to df dx dx dt. This is a chain rule. It says if you got two embedded functions, the derivative of the inside dummy variable is the derivative of f with respect to x and then x with respect to t. So each of these time derivatives are going to give you separate terms. Work on that. y, dya dt plus d. And this is equal to UA, this is equal to VA, and this is equal to WA. So simplify that. You get DUA dt plus UA du VA DUA dy plus WA. This is also in the book, so you don't need to feel like you need to get it. The next one. All right. So the shorthand for all this says this. Acceleration A, in general, is you've got a moving velocity field as a function of space and time. It's a material derivative. That's a shorthand. Some people call it the substantive derivative. And basically, we use the definition at capital D by dt. First, you have the partial derivative, and then you have the convective one. U d dx plus v d dy plus w d dz. And that's what this comes from. So again, this is the time-dependent part because the entire velocity field became changing at once, and this is basically convective derivative. The change the results for going to different places in space where that property is different. Okay, now let's use that to solve this problem here. That time-dependent part can also be considered the local acceleration. All right, so the local acceleration from parts 1 to 2. Well, du1, basically, if you just take the derivative of the first one, the second one, with respect to time, du1 we're going to do 4. du2 dt is equal to 2 feet per second squared. Feet per second squared. So I guess I shouldn't call it from 1 to 2 at points 1 and 2. So basically, it's accelerating more in the beginning than in the end, just because of those time-dependent parts. Now the convective acceleration. Call it u dot del. Now this is a one-dimensional problem. Generally, we have u is equal to u v w, and x is equal to x y z. But in this problem, everything's 0 except for u and x. And so u dot del, which is originally 3 terms, the 3 terms you saw on the other side, u times d dx plus d whatever. So here we just have u times du dx of del u. And that actually has the units of acceleration.
Dr. Hu, I have a quick question. How do we know that V, W, Y, Z are 0?
Because this is a 1D problem.
Okay.
Anytime fluid is just basically going horizontally in one direction, you don't have any vertical components. You don't have anything going into the page or upward.
Dr. Hu, could you potentially go back to the board where you're doing the convective acceleration?
Yeah. This one?
No, the board 4, please.
Oh yeah, this one.
Yeah, perfect.
So, just to review, basically, d by dt is an operator, and but the thing that you're really going to be operating the most, at least for the linear momentum, is basically operating on u, velocity. For conservation of mass, would be operating on the mass. Conservation of linear momentum will operate on linear momentum. Angular momentum will change what's going on in there. But if you want to consider the acceleration from point to point, you really want to plug in the u into that. So it looks fancy, but all it is that you put in something and you'll get something out. This is called a scalar operator. That means it doesn't. If you put in a vector, you get a vector. If you put in a scalar, you get a scalar. It just basically spits out some new value based on what you put in. And to spit out that new value, what it does, it says, well, you first take the time derivative, and then you take the velocity at u, v, and w, the horizontal and vertical, and multiply by then how much the fluid is changing in this property in the x direction, y, z. Yeah.
So if you asked to find the total acceleration, you'd add the local and convective acceleration?
That's right. That's right. Because they're independent parts.
Dr. Hu,
Yeah.
Could you just move it to board 3 and then move the that light thing? It's kind of in the way.
Oh, you keep it on board. Oh yeah, let me.
The light that I can't see the bottom part. Thank you.
That looks pretty safe. That thing has not worked at all during the semester. I think the technologists cannot keep up with that stuff. All right, so to do this problem, you're going to have to basically calculate. So you're just asking if it's greater than, is it positive or not, negative? Because they didn't really give you one point in time. So is it accelerating or is it decelerating? That's the question, due to the diffuser. I guess when you put it that way, the answer becomes like more clear. Who thinks it's accelerating? Who thinks it's decelerating? Why do you guys think it's decelerating?
Going slow when it comes out.
Yeah, okay. And you can get that from this. And the reason is because this du dx is negative. It's basically v2 minus the v1, and the velocity. Or I shouldn't be changing from v to u. The velocity minus u1. Velocity u2 is smaller than u1 always. So no matter what length this is, we'll call this a length L. No matter what length this is going to be less than 0. And as a result, that's less than 0, and this is less than 0, and this is going to be less than 0. So, and this is because at any one time, u2 is less than u1. All right. Okay. So now you know, you have an idea of what convective acceleration is, which is always calculated between 2 points. All right. All right, we're making a lot of progress. You need to know that concept of convective acceleration because you should have an intuitive idea of Reynolds transport theorem. That's what we're going to do now.
Professor?
Yeah.
When you calculated the convective acceleration, you didn't include the d dt term because it's it's constant flow, or is it?
It's just this is a terminology thing. So someone asked earlier, the total acceleration is basically going to be you have this term plus this term. This is called the sort of local or the time-dependent part, and this term on the right is convective. We only call the term on the right convective. Convective, you've heard of convection ovens. Convective just means from going from place to place. Because the only reason things are changing is because you're going to a different location. Going from point 1 to point 2. You're looking at the change due to going from one point to another. This one is just due to the fact that everything's decreasing in time, or in this case, it was increasing in time. This is happening everywhere, and this is happening because you went from one place to another. We'll do more examples of convective acceleration, but it's due to the fact that the velocity is different on the right than the left. So, because of your convecting, things are different. All right. So I've been throwing around these terms of the control volume. We got to define it rigorously. So these, otherwise the Lagrangian equations start to not make sense. So that problem basically ended my discussion of chapter 4. When you do the study for the quiz, maybe just scan through chapter 4. Really, the quiz problems are going to be from chapter 5. But you kind of have to know what these terms are before you get to chapter 5. All right. So there's basically two definitions that you need to know. One is the system, and some of you are taking thermodynamics. The system gets back to where we tag stuff. Of tagged matter. So it's like you marked it red. Or in more formal terms of fixed identity. And the control volume is a useful tool to understand what happens in that system. And we necessarily want stuff to flow in and out. So it's a volume in space. So control volume, the keyword is a volume. It's like you put little dotted lines and you keep those dotted lines fixed in space until we do what's called moving control volume problems. But don't worry about that until first. How much fluid may flow, and then control surfaces. And control surface, as it sounds like, is the surface of control volume. I'll be using notation CV and CS, just otherwise it's going to get lengthy. Now the thing about the system, it can change in shape and size. You know, if it can decrease in volume, like if I'm pressurizing something, but it's basically still that same fixed quantity. All right, so Reynolds transport theorem is the backbone of all the things that we're going to do. To be honest, I'm not going to be talking about Reynolds transport theorem in the quiz, but all the Lagrangian equations that we're going to use are from here. So B is going to be, capital B is going to be some fluid property, something that has units of mass or momentum. So we'll call that extensive because I don't need to know how much of that I'm talking about. And then I'll call little b is a property is that same property per unit mass. And whenever we do something per unit mass, we call that an intensive property. And Reynolds transport theorem says this. Again, we have the material. So let me just box this. This is what we're going to be. We won't derive it rigorously. I'll just give you a little sketch, tell you what these terms mean. But again, just like the definition of material derivative, there's two aspects. One that's a time-dependent part, and one that's due to convection, going from place to place. So this dB system dt, let me leave it there so people can copy. I'll erase. And I will say, this is like, I'm going to give you, there's a huge amount of firepower in these equations, but you're only going to be using a little bit of them because we'll be generally doing things that are constant velocity along cross section. So anytime you're going to do an integral, it's generally going to become a product. All right. So physically, this is the time rate of change. So of course, you remember this is the material derivative of how much the capital B is in my system. And what it means physically is the time rate of change of B that is transported by fluid currents. So if I were to mark, for example, the original warm-up problem, I have a fluid in the pipe. If I wait some later time, it's going to the right. And as it does that, things are going to change. Oh, I got to write one more thing. So the equation, I got to label this. This equation is Reynolds transfer for fixed, non-deforming control volume. There are some years I put the deforming control volume, but I consider that to be actually much more difficult than the non-deforming ones. So just try to master the stationary control volume first. All right. So why is this thing true? Well, it first starts with the definition. How much capital B I'm talking about, and let's say we're just talking about mass, like how much B weighs. Basically just given by this derivative, where rho dV is equal to dm. Basically, I basically, consider how much B is taking up, and I figure out how much little b there is, and then I just multiply. Okay. So this is just the integral, the derivative of this integral. Will be dv. And I can do the same thing with the control volume. Just take the derivative with respect to time. All right, now the picture I'm going to take away is this, board 4. The picture is that basically you're going to have the convective harm you consider as fluxes from a zone that's leaving and the zone that's coming into the fluid. So lemma just means like kind of like a little thing that's useful to know to prove the entire thing. All right. So let's consider the warm-up problem. That's a variable area pipe. All right, I actually got to use 2 colors, so it's super clear. I'm going to have to use green. All right. All right. So the dotted lines are going to be the system boundary at time t. It's also going to coincide with my control for surface. So I'm going to keep my control surfaces on this dotted line, and my system boundary is going to start there. Now, later, with the green, it's going to move, and things are going to change. So this is the system boundary at t plus delta t. Okay. So, and you can sort of distinguish it. You can write those into kind of, I'll draw another diagram here that kind of summarizes that. So the original one was CV, and then basically I can call this, I can label these 3 parts the following. The control volume minus this part I is this one in the middle. The part I is on the left, and the part 2 is on the right. And those are going to represent sort of 3 different volumes. So to make it super, super clear, we'll have this table. At time t, the system is equal to the control volume. At time t plus delta t is equal. The system has changed its basically it's lost the part on the left, and it basically to track the original volume, I've got to add basically part 2 and subtract part 1 because I'm over counting. Okay. So at time t, the system of time is equal to v control volume of time, and then at some small time step, So it's basically kind of like I'm using my control volume to tell me what my system's doing. But I got some errors. Because my control volume, I've got to subtract out the part 1 because the system's no longer there. And I've got to add the part that the system has moved to the right. That's what this sort of error term means, minus B1 plus B2. All right, let's go to board. Let's erase this. We only got 2 steps left to get to Reynolds transport theorem. And the stuff that's been basically the stuff that's leaving through the control volume, you consider what people call those fluxes. All right. So we've defined what V system at t plus delta t and at t. So now we just do the definition of derivative. So as delta t gets really small, right? And we're just going to copy what we wrote. And we're going to substitute in for B control volume, so they coincide. And that gives us the following 3 terms. We got limit all right. All right. So those 3 terms are dV dt plus what we call capital B out minus B dot n. Those are the flux terms. The stuff that's leaving the control volume on the right is the out. I'm sorry. The stuff that's leaving, that's basically sort of leaving on the left is the out, and then with stuff coming on the right is the. No, I was right the first time. So on the right side and the inside. Okay, and this is basically the Reynolds transport theorem. It's sort of a non-rigorous way to write that. The only difference is that the Reynolds transport theorem has actual flux terms, where this B out basically writes the terms in integral form. So this is integral of rho B dV dV, right, dt. And these are going to be flux terms. These are going to be integral rho B u dot n dA. Yes. Yes. So I'm going to put 2 of these arrows because basically this integrating the whole control surface, but we're splitting it in 2 parts, the influx and the outflux. All right. Let's start an actual physical problem. So this idea of the time-dependent part and the flux in and out, we'll be using that over and over. And we're going to be tracking different quantities. The simplest one to describe is conservation of mass. So they also call this continuity. All right. It's saying that wherever we draw our control volume, the system that we're considering is not going to be changing in mass. You're not basically destroying fluid or creating it. Where the mass of the system is going to be integral across the original control volume, where they're coinciding with the system of the density. And if we use the Reynolds transport system with a B equals mass, and the mass per unit mass, the intrinsic quantity for mass is just the unity, just 1. All right. So Reynolds transport theorem with B is equal to mass, you get this. Let's talk about what these terms mean. So this, the left-hand side is the time rate of change. So this is system. Rate of change of mass of system, which is going to be 0. This is and the rest of, so everything on the right-hand side is going to be using a control line. The system is kind of an abstract quantity. You know what it is in space, but it's very difficult to measure because it's moving. So that's why we use the control volume as a tool. So this middle term is time rate of change of mass of CV. The flow of mass through the control system. All right. I call it the net rate because in Reynolds transport theorem, it's got basically a part that's going to be influxing and a part that's outfluxing. So it's basically the sum of all those parts. The book will, and for a lot of problems, to be honest, you can have a shorthand way of describing this integral as m dot out minus m dot in. Okay. And so if we call this equation 1 and equation 3, you find 1 and 3, you get the version I'm going to give you on the quiz. Rho dv plus cs rho du dot n hat yay 0. All right. This is conservation of mass. We will do it with, this is with fixed control systems. We'll do it with a moving ones, probably on Friday or Monday. So again, this equation doesn't give you any forces. It only gives you, allows you to track how much things are changing. So I'm going to start drawing this, and then we'll maybe finish it next time. So this is the leaky syringe problem. All right. So this is leaky syringe. So the question is, you're trying to figure out the rate of the plunger, the speed of the plunger. So we'll call this UP. Oh yeah, let me move it. Given the area of the plunger, let's just give some units here. It's like 500 millimeters squared, and so it's leaking out at some volume per minute, 300 cubic centimeters per minute on the right, and it's also leaking out 1/10 that amount on the left. So how do you use the conservation of mass equation to solve this problem? Well, let's write that equation here. All right. So this is going to be equal to 0. All right. Now, the control system, first to properly define this, the control volume, kind of draw it like this. And so you can see there's most of the velocity at the control volume is 0, except for two parts, one there and one here. Basically, it's leaking out towards the right. That's what it's supposed to do, and it's also unfortunately leaking out a little to the left. So this, like I said, most of this quiz is not going to be actually evaluating this because we're going to assume it's constant velocity, or you can just assume what this means physically is the flux of mass dm dt through each of the sides. So we'll call this m dot 2 plus rho times q leak. M dot 2 is the mass flow rate to the right, and rho times q leak. Q leak is the volume per time. Rho times q leak is the mass per time. Okay. And this is also equal to m dot out, and we have m dot in. There's nothing coming in, so in this case, m dot in is 0. Okay. Yeah.
Is Q2 equal to Q out?
Yeah. Yeah, we can just call this Q2. Thanks. So you can see where I'm going to be going with this, because I'm given rho, I'm given Q2, I'm given Q leak. Now I got to figure out this left-hand side. Integral of rho dV equal to integral of we'll call that L of t times A. So A is going to be the cross-section area here, and this thing is changing. It's going to be sort of squeezing because it's decreasing. And so the time derivative of this, d by dt of this is equal to d by dt of this thing. And that's going to go rho a dl dt. That's equal to negative rho a v u plunger. Because we assume the velocity of the plunger is the magnitude, so going to the right, and L is decreasing, so L is necessarily negative. And altogether, this gives us negative rho A UP plus, so m dot 2, I'm going to call that Q2 times rho. So together, plus rho Q2 plus rho Q leak equals 0. So that gives us a closed form equation. And that says UP is equal to Q2 plus Q leak over the area. We'll just call it A instead of A sub P. Okay, so there were two parts of this problem. One that you figure out the two outfluxes, rho Q2 plus rho Q leak. The other one, you write the integral of how much stuff is in the control volume. That's changing with time, so we invented this variable L, and then we substitute. We know that L respect to the derivative of L respect to T is equal to negative U sub P, and then we just solve. So once you basically write down this, basically what the integral is, the rest of this is just turning the crank. All right, sorry, I'm a minute over today. So next time we will do 2 more control volume masses, and we'll start controlling linear momentum. Linear momentum, we're going to need to consider both x and y velocities. So you're going to need to have like double the number of equations for each of those 2 components. So we'll need to have an action-packed Wednesday and Monday. If you can come to class, I would suggest you come to class. So you can sort of really absorb as much of the material before next Wednesday. And if you need any old quizzes, they're in my office. I'm going to go there right now. Yeah. Okay. So physically, okay, what is these units? This is V dot, and so rho V dot is, well, this whole thing is m dot, because the u times n, that's going to give you dv dt, but this whole integral means the m dot net. So m dot out minus m dot in. And m dot in was 0. So basically, if I were to draw like little arrows coming out, that's u. N is also going outward. So u dot n is just u dot n times rho times a. It just gives you your mass flux out. This has units of volume per time, and this has units of density. So that's where we get mass. So in this problem, because we don't have any influxes, u and n are always in the same direction. So u dot n is just going to equal to u. When we do an influx problem next time, you're going to have, then the sign actually matters. Then we're going to have a negative sign. Yeah.
So m dot 2 is different from the m dot out.
No, in this case, m dot out is all the things that are going out. So m dot out, basically there are 2, all right, I don't know if you can see this, but we call this basically this flux term composed of 2 things, m dot out minus m dot in. And there's nothing going into the syringe. There's no input to the syringe. There's only leaks. M dot 2 is then separated into 2 locations, that location and this location.
Can I ask?
Yeah.
Question?
Yep.
When So, but this was between 2 points because you're taking basically it's the average. It's
Oh, you also wrote it's 4t feet per second, and that's 2t feet per second.
Oh, okay.
And that'll help you a little bit.
But and then.
And because this velocity, 2t is always less than 4t, ut is always less than u1.
But dot
Yeah.
times, even though it's one-dimensional,
So you would probably use the average u between those 2 points.
okay, it's not just u at a point. Like add a
Well, this would be this. You can only really convect it have this calculate this on an average sense.
Okay.
So you take the average u between those 2 points would be 3t. But the thing is, u is always positive because it's always multiplied by time. So you got a positive number multiplied by a negative number, and so the thing's going to be negative.
I was just confused if that was supposed to be a value at a point or if it was
In general,
an average between.
so in general, you calculate this thing at a point, like at a point x. And so if you're to do that, you'd have to calculate like how much the velocity is changing at that point. We'll call that x naught, plus u at x naught dot del u of x naught. So you'd have to calculate the velocity at x naught. So it is true, you calculate them at points. But for this one, they didn't actually tell you what the middle value was, so you kind of had to just do the average. And that one, they just asked you, is it positive or negative? Yeah. Oh, yeah. Yeah.
Right, I would talk to you now, but.
Yeah, let's talk about it on Wednesday. Yeah, sure.
Professor, so what does the n actually represent?
N is the normal vector. So if you've got basically an arbitrary surface, n is the outward normal. So for example, for that particular syringe problem, we have n always going in the same direction. The whole thing, we have a sign of positive for outflow is because n and u in the same directions when stuff's going out. When n and u are in opposite directions, you have a negative sign. That's why you have a negative for this n dot in. And that's just arbitrary. We just always call it outward normal. There's a lot going on in this lecture. This is like pretty dense.
Yeah.
This is like the hump of the course. There's nothing to prepare you for what's going to happen in the next 4 weeks. But there are some classes that actually start with this. This is like the first day class.
Really?
Some class, there's some classes they start with the Navier-Stokes Equations, like hit you with a bunch of calculus. I kind of try to save you, and wait for the calculus until now, but I can't save you anymore. So I think the physical part of it is more important than the math part, but you do have to get to both. Yeah, we call that flux, but it has units of m dot, has units of mass per time.
But this is rate of change
in the control plane. So that so it's basically everything in this green dashed line. We're talking about how much that's changing in time.
Okay, because it seems kind of so.
They look pretty similar. That term.
These things kind of cancel, and that seems like just volume. Mass.
Yeah. The key difference is this is integrated over a surface, and this is integrated over the volume.
Okay.
So this one doesn't even see what's inside. This one only sees what's inside. For the plunger problem, For the plunger problem, the thing is everything in the green spots is decreasing the volume, and that's what we calculated on this part. And also stuff's leaking out the two sides, and this is just saying, well, how much is changing inside the plunger is equal to what's leaking in and out. It's conservation of mass is very intuitive. Basically, the only way stuff can be changing on the inside is if it's leaking out through those two sides. And you just have to be systematic and keep track of those two sides and get the units right. But that's just the general form, because There's some complicated questions that have moving control volumes that we'll do next time, that you do need to have that form, the general form. All right. Okay, Blue Jeans World, I totally neglected you guys, but it looks like you have no questions on chat anyway. Wow, they absolutely have no questions. I wonder if anyone came today.